Hi, AP Stats. This is the start of Chapter 6, so this is our notes for 6.1. Two vocabulary words. We're going to talk about the difference between discrete and continuous. We're going to talk about random variables in just a second, but a discrete variable is something that is countable. So it's usually something that comes in whole numbers, so like numbers of shoes, numbers of pets, numbers of people. Right? We generally don't talk about having 1.2 pets, right? So it's countable things. Continuous random variables are those that could come in fractions or in decimals. So like your height, we generally round to the nearest inch. But if we didn't want to, we could even break it down even further from there. So that definitely can come into fractional or decimal amounts. Your weight, we usually round to the nearest pound, but we don't have to. How about the distance you ran, right? That doesn't have to be always done in miles. It can be done in fractions of miles. So continuous random variables are those variables that usually can include fractions and decimals. It's kind of like on a number line where you'd be able to color in everything from like 0 up until a number. And a discrete random variable, so let me draw that. So like if I had a 0 here and like let's say the maximum height was 8 feet, right? We would have some people that would end up on all of these numbers all the way up to 8 feet. Right? And there might be more people in a certain area, but we'd definitely be able to count all of those numbers from, well, okay, maybe not 0 as a height, but you get the general idea. All right. And then in a discrete one, if I was counting the number of shoes, right? If I was counting, let's say, let's do like numbers of pets. So maybe the max there we would get would be 8, but there are some people who have none, right? So then we would be looking at you either have 0 or you have 1, or you have 2, or you have 3, and so on, but I'm not going to say I have 3.5 pets, right? So there's gaps in between there, between those counting numbers. So the difference is continuous is kind of like coloring in that entire number line, and discrete is like counting each one of those numbers on the number line. All right, so let's talk about the variable word that you do know. That's the algebra variable word. It happens to be x, usually it's lowercase x. And it's a constant. It's some number that we don't know yet, but we could solve for it. So all I would have to do to solve for this, obviously, subtract 3 from both sides, and we have now found what x is. X equals 7. This is now our known value. We have solved it. It is always going to be 7 in this problem. It's never going to change. It's a known value, right? The ones we're going to be working on are going to be capital X's, and they're going to be called random variables. They're still numeric. But it's talking about something that maybe hasn't occurred yet. So there's many possible answers for x. It's not just one answer. So we usually use an uppercase x, so maybe it would be the number that I win, right? So maybe I win $10, maybe I win $20, I don't really know. How about the number of people that earn an A? Well, at this point, I don't know how many are going to earn an A by the end of the semester, right? So it's a changeable number. It's something that can change. So I might be able to calculate the percentages of what's the percent of one person earning an A, all the way up to what's the percent of all 36 people earning an A, right? And all of those would have different X values, X being 1 for one person, 36 for 36 people. So capital letter usually indicates that it's a random variable. All right, expected frequency. That's just telling us how many times do you expect to get something, to have something actually occur. So let's talk about the chance of winning Monopoly. I've talked to a few of you before. I don't remember if it's your class or not. My daughter is fantastic at Monopoly. I cannot beat the girl. I just hope for bankruptcy most of the time, honestly. So maybe I'm lucky. Maybe she's nice to me. But about maybe 2 out of 35 games or so, I might win. So if I play 300 games with her, how many games should I expect to win? That's an expected frequency. So how many games would I expect to win? So let's see, what would I do for that? I would want to try to figure out what is the probability that I would win. So if I win only 2 out of every 35, and I'm going to play this game 300 times, then that's going to give me 600 over 35, which is going to turn into 17.14. So if I play this 300 times, the estimated amount of games I'm going to win is about 17 games over 300 games with her. All right, so that's expected frequency. It's just kind of saying how much do you expect to get based on this probability number, this probability fraction. All right, that leads us to some probability tables that you've already seen, you've already created in the past. Okay, so we're going to talk about those dealing with random variables. So we're going to talk about this idea of a roulette wheel. So the probability table is just a table that includes the probabilities. Probabilities are usually on the last row. And then the top is usually the random variables of things that can happen. So we're going to start without a random variable just to get a probability table going. So in the game of roulette, there are a total of 38 different segments on a roulette wheel. And of those 38, 18 are red, 18 are black. 2 of them are the green ones that are on the left and the right. Those are the 0, 0, and the single 0 sides. So if I wanted to do a probability table over these, I would want to know what the grand total is for this. It is 38. So what's the probability of getting a black? Well, it already said there are 18 that are black, so 18 out of 38. It already said there are 18 reds, so 18 out of 38. And then there are 2 out of 38. Okay, and I can go and calculate the decimals of this, but again, they're going to ask you, is this a valid probability model? And we've done this before. What are we looking for to make sure all the probabilities are between 0 and 1 and that the total sum is equal to 1, right? So each one of those fractions is somewhere between 0 and 1. If I add them all up, 18 plus 18 plus 2 is 38 over 38 as a total. So this is a valid probability model. If we were to play this game 100 times, what is the expected frequency of getting the green? Okay, so again, expected frequency is how many greens do I think I will get? So if my chance of getting a green is only 2 out of 38, and I repeat this 100 times, that's going to be 200 out of 38, and 200 out of 38 is about 5.26. So we expect to get green about 5 times out of 100 games. Okay, that's how you interpret it. We expect to get green about 5 times out of 100 games, all right? Suppose I decided to look at a probability table to explore how much I'm likely to win at one of these games using roulette. So now notice that we have a random variable has made its appearance. Here it is X, and X is now defined as the amount of winnings. Okay, so how many of these am I going to win? So now we have random variable X is always our numbers. Okay, and then the probability underneath them is how likely it is. So we're going to take a look at black this time. So I'm going to say that if I end up on black, I am going to win $100. If I end up on any other color, I'm going to lose $100. So now they're not having me break them out by just red, green, and black. They're just black and not black. So this is all the other colors. So if I remember right, black was 18 out of 38. That means all the rest goes into the table over here. So we can see that it's more likely that I'm going to lose money than I'm going to gain money. They're both still valid probability models. Each fraction is between 0 and 1. If I total them up, I still get 38 over 38, so I'm happy with that. Okay, so we're going to go and try to calculate the average, the expected value. Okay, so expected value is just your average. It's another way to say mean of a random variable. So if I wanted to go and find the average variable or the average for this, the expected value, I would go and I'd take these, let's turn them into decimals. This is 0.474. This is 0.526. So let's take a look at these. So if I only have a 47% chance of earning $100, 0.474 times $100, and I only have a 52.6% chance of losing $100, they're not equal. I can't just say it's going to be a 0, right? It's more likely that I'm going to lose money. Well, how much more on an average play am I expected to lose? So if I look at these and I move them twice, this would be 47.4. This would be negative 52.6. And so if I put those together and I add a negative, I would end up with losing $5.20 per game on average. Now, obviously, I can't lose $5.20 on one game. I'm either making 100 or losing 100, but my expected value is a long run average per game. Okay, so the mean per game is negative $5.20. So let's say I played this for 1,000 times. What would my average winnings be per play if I did this for 1,000 times? Well, then I would just look at how much am I expected to win, 0.474, it's gonna get really repetitive here in a second, times 1,000 plays would be, I would expect to win 474 games if I played 1,000 times, and then 0.526 times 1,000 games. So my frequency would be 474 for wins and 526 for losses. That's my that's my frequency. Okay. Then what are my expected winnings? Well, now I have to bring in the $100 that I make or lose. So if I win 474 games and each one earns me a positive $100, that's 47400, that's $47,000, 47,400. If I have an expected loss, that would be my 526 games where I lose $100. So that would be 52,600, but it would be negative money that I would lose. So what's the average winnings? Well, again, if I'm doing 1,000, I can go calculate it as 1,000, figure out what the difference is between these two. So here is a 2, here is a 5. So it's 5,200, but that's over 1,000 games, and it should be no shocker that the average amount that I would lose per game is about $5.20 again. Okay, so this is just including the frequency one. So here is my frequency, right? If I played 1,000 games, my expected number of games that I win would be 474, and that I'd lose would be 526. Okay? Interpret the expected value of playing roulette. Okay, so my expected value of winnings playing roulette. Okay, so remember that this is a long-term average. This is something that we're expecting to happen many, many times. So I want to include those words again. So after repeating many, many trials, the average winnings in roulette is a loss of $5.20 per game. Okay, so I want to include that idea that this is a long-term average. If I did this many, 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 many times, then I'd end up with losing about $5.20. Now, I could also say my average winnings is negative $5.20. Just don't say that you're losing negative, because then you got the double negative thing going on. All right. So when we calculate expected values, it's kind of like a weighted average. So we do this in a lot of math classes, and your scores will say like 60% of your grade is tests and 40% is homework. This is the same idea of weighting scores for that. So let's take a look at some of the weighted averages that we can do. So here's another example. Let's say we played a game that involved tossing a coin. Okay, so it's a fair coin, so we are expecting it to be 50% of the time heads, 50% of the time tails. So that would be half of the time it's heads, half of the time it's tails, and this would be 50 and 50%. So heads means that I get $400, tails means I lose $200. Is that a valid probability model? Each individual one is between 0 and 1. Yes, they add up to 1. It is a valid probability model. I can continue. All right, so we want to go and calculate the expected value of this. So the way we write this is we say it's the expected value of X. Capital E is expected. X is of the random variable. And we're going to do a weighted average. So we're going to take this 50% and multiply it by the 400. So if half the time I am winning or $400, that is a grand total of $200. And then I'm going to add the next one, which is 50% of negative $200. So half of $200 is negative $100, which is going to turn into $100 positive. Okay, so $100 positive. So my expected winnings are $100 per game. Again, on average, after playing this game many, many, many times, on average, this would be a good game to play. I should win overall about $100 every time I play this game, on average. That's a pretty good deal. All right, so what happens if we're going to come back and talk about this again with probability tables, but we're going to add in a couple more. So if we're already talking about mean, okay, and by the way, we want to add in one more thing here about mean. I will do it down here again below, but expected value is also another way to say mu. Remember, this is that Greek symbol. So mu sub x is another way to say the same thing. So capital E parentheses x is the expected value of random variable x. Mu sub x, it's a capital X, it's just a subscript. It's still saying the same thing. It's the mean or the average of random variable x. Okay, so if we're going to talk about means, we may as well talk about variance and standard deviation at the same time, right? Those kind of go together. So remember that there was a relationship between variance and standard deviation. So if you if you're trying to find variance and you have standard deviation, square it and you get variance. And if you're trying to find standard deviation and you only have variance, take the square root, right? So variance is usually called sigma squared. That's a little like O with a little tail at the top. And then standard deviation is usually just called just the little sigma. Cool? All right, so we're going to go back to that roulette example again where the 100 is for black and the other one is for other colors. So that's the red and the green. Okay. So if we wanted to find the expected value here, same exact deal. We take each probability, we multiply it by its random variable, right? And we get 47.4. And then this becomes minus 52.6, which turns out to be negative $5.20 on average per game. So this would not be a game I would want to play, right? Because on average, I'm going to lose $5.20 on average every time that I play. But let's take a look at the spread. Is that pretty like consistent? Is it always $5 or is it like wildly varying? Like sometimes I win a whole bunch and sometimes I lose a whole bunch and it kind of averages down to -5. That's what variance and standard deviation does for us. All right, so reminding us what the variance formula is, and this is dealing with when we have probabilities, weighted probabilities, okay, is we're still going to go ahead and we're still going to take whatever the random variable is, subtract it from the mean, and then square it. So every time there's a number in the table, that's the positive 100 or the negative 100, it's going to create its own part of the calculation. So you notice I have positive 100 minus my loss of negative 5.2. And yes, that's going to turn into 105.2. And then I'm going to square it, and then it's only going to carry a little bit less than half the weight of the probability, 0.474. And then I'm going to do the same thing with the negative 100 minus a negative. Now that's not going to turn into 105, that's going to turn into 94.8 as a negative and square it. And that's going to carry a little bit more than half the weight. Okay, so when I put all those together and I calculate that all the way across, I get variance. So in this case, I would get this amount right here. So the first number gave me 5,200. The next time after the plus sign about 4,700 for a grand total of 9,972. Now that doesn't mean a whole lot to us in applying it to the problem, but if we're just going to do a lot of comparison and see which ones have larger spread, and I'm comparing to something else, I don't really need to go all the way down to standard deviation. I could compare things at the variance level if I'm comparing it to something else. So that's why we call it a convenient measure spread. If I'm just trying to compare it to somebody else's spread, I can stay in variance and not have to take the square root. We're going to go ahead and take the square root because we don't have much to compare this to. So if I take the square root, I end up with 99.86. This is the typical or the average spread from the mean, same definition that we had before. So on average, playing this game of roulette, I'm going to lose $5.20, give or take $99.86. That's a huge range when we're only talking about plus 100 and minus 100. So they're basically saying it's going to vary almost $100 either side of $5.20 of a loss. So I could be off when I say I'm going to lose $5.20 on one game. I could be off by almost $100. That kind of makes sense, right? Either I made 100 or I lost 100. Okay. All right. So we've got those going on. So we've got mean, variance, and standard deviation. All right. Let's do one more that's a little bit different. Same basic process, just a little bit of a different format and a little bit of a different setup. So on this one, let's say that we had a spinner, you know, one of those ones that you flick with your finger, okay? And it's got 4 equal parts. They're numbered 1, 2, 3, and 4. And in this game, you'll win $100,000 if the spinner lands on 1, but you'll lose $40,000 if the spinner lands on any of the other parts. So now my random variable is still my winnings, right? And the probability is I have a 25%, right? Only 1 out of the 4 pieces of the circle, a 25% chance of winning the 100,000 and a 75% chance of losing 20,000 instead. But that doesn't sound so bad, right? Because I could either make 100, which is a lot, or lose 20, which is a lot, right? So let's find the expected value of the mean of the random variable x. So expected value, E sub x, also known as mu sub capital X, and it's just the weighted average. So we're going to take the 0.25, multiply it by the 100,000, add it to the 75%, multiply that by negative 20,000. Okay, and if I do that, I should be at, let's see, $25,000 minus $15,000, which would be a positive $10,000. So on average, if I were to play this game many, many, many times, my average winnings should be about $10,000 per game. Okay, that would tell me since it's positive, it'd be worthwhile to play, right? But maybe I should look at how much that's going to vary. So if I'm on average going to make $10,000 a game, that's pretty good. Let's go see if we can find the variance. So the variance says I'm going to start out with, so let's do variance. So variance is equal to sigma squared. And I guess they call it variance sub capital X too, same idea. Okay, as I'm going to start out with the random variable x, 100,000 for the first one. Subtract out the average value or the mean, so subtract out 10,000. Square that, and then multiply it by the weight. And then we're going to do the same thing to the next one. So that is negative 20,000 minus 10,000 squared times the weight of 75%. Okay, and I'm going to add those all together. And so if I do that, this will end up being 90,000 squared, and then times that, it ends up being 2025, 123, 123. Okay, and then the other one ends up being plus 675, 1230s, 1230s, for a grand total of 2700, 000, 000 is our variance. And then if I want to go all the way down to standard deviation, take the square root of that, and I'll get, give or take, 51,961.52 cents. So that is my typical spread from the mean. Okay, so that means that on average, I should be making $10,000 a game for playing this, but I could be off by as much as plus or minus $51,000. Okay, so keep in mind that we've done one where the average was only losing $5.20 all the way up to that we could be making $10,000 a game. And again, think about this idea of when we were talking in probability about long run averages, right? If I'm on average going to lose $5.20 and it doesn't vary that much, it's pretty typical. I kind of know when I go into play, I'm going to lose about $5 a game. And for some people, that's worth it for the enjoyment, right? And maybe I only play 10 games and I lose $50, and maybe $50 isn't that much. Great. But remember that on the other side, if I'm losing money, somebody's making money. And that somebody that's making money are the casinos or the places that are doing that type of gambling types of stuff. And they're definitely working the long run averages. You might only sit down for 10 games, but they're collecting at the end of the day thousands of games where they're always winning by a little bit more than 50%. So long run averages for the casino is that they make money lots and lots and lots. And we see that same false probability idea of, well, I haven't won in a while. I am due to win on the next game. It's going to happen. It has to. I've been losing for so long. It's got to happen. So this gives you some kind of feedback into not only what the probabilities are, but how much money that could end up to be at the beginning or the end. All right, so that is it for 6.1. We'll see you next time. Bye, guys.